So, hello to everybody. My name is Čeněk Jirsák. I hope you can hear me. You can see everything. We will be speaking in English because why not? But the annotation is in Czech. And first thing I would like to talk about is the annotation itself, because I don't know if you read it, but the abstract isn't very good. But I really noticed, so it's no problem. But the thing is, it was generated with ChatGPT. So I was actually this is how the AI will do it, because I was just curious if anybody would notice anything. I don't have the exact prompt, but it was something like this. This is what I wrote. Basically, what I want to talk about, and I get a response in Czech. It's not even the latest. It's usable if you read it. There's plenty of things that could have been better, but I was just curious how it will go. So you can have a look afterwards. The other thing is, I was because my topic is inspired by a reliability exercise, and this I will show you on the picture. So the beginning is motivation, and we will go through all these steps. We will spend pretty a lot of time defining the model, and then we will talk about different variations of the model throughout the presentation. And so the industrial motivation is pretty much 10 years old, and I was on an internship in Stuttgart University, and we were trying to optimize some maintenance decisions in a power plant. We were considering this small piece of the plant, so it was this is like, I don't know, 5 meters tall, so it's pretty tall on its own, but it's a refraction of the whole installation. But I think it's already 10 years from the internship, and the factory, the power plant was closed in 2016, which is also like 7 years from now. So I think it's like the motivation is pretty much long gone. But that is the setting. The idea is that we would like to model the system with more than just working and failed conditions, and because the usual models consist of just two states. The component is working or fail, and we will be working with model with parallel redundancy. This means that if you have some kind of component that you need, for example, seven mills to run the power plant, but you will build 8 because you want to be safe. You want to have some redundancy, because usually if 7 mills are running, the eighth one is under repair or something like that. So this is how we did it back then. This is how it was done. This is just for 2 mills. You have 1, 2, 3, and you have like 2 dimensions, because there is you have 3 stages for performance and 4 stages for condition, and you have, like in this big picture, so like this, the state of the first mill, and then you have another 12, and that's the condition of the second mill. And when you know how good the condition and the performance is, you can make a decision based on it's just what we did back then. For example, this is do nothing. If you have both males in like brand new performance and so on free, and condition is so small, then you just do nothing because you have a new system. On the other hand, if everything is failed, it's just replace anything. Oh, and the idea is that we want to go from this two-state model into the multi-state model, which was the picture before. And it might seem like a good idea to have a lot of steps on the way, but it's not really the case, because if we have some kind of random variable, we have exponentially distributed these steps, and we fix them that the time to fail is this big T. So we have all these steps. We have n steps here that the component must go through before it's destroyed. So if we do it with exponential distribution and we sum it up, we get gamma distribution. And gamma distribution, if the n is large, it basically looks like normal distribution. So, but the problem is that the variance of the distribution goes to 0 as you increase the n. And it's, so what you will achieve when you have some kind of random behavior and you're adding up small pieces is that you just mitigate the variance. So it's not a very good idea to go with something like this and say, okay, there will be some random time, and then we get there, and then we get there. And if we have 5 steps, then maybe with 10 steps it will be better, but it is not. You're diminishing the. If you have a constant expected value, so the expected time to failure, and you just drop sizing these steps, it will make the variance go to 0. And this is pretty much the case for any random variable, since you don't have to start with exponential variables as long as they're ideal. They have to be at least independent. I'm going to from central limit theorem, you get similar results. It will not be exactly gamma, but it will, as long as you have reasonable random variables, finite variances and everything, then it's the same case. So what we would like to have for this determination process is something that is non-decreasing, because non-decreasing, so something like this, I would imagine some component, and it just looks like that, and eventually you see some kind of threshold. If I want it to be non-decreasing, you have to increase. This is the non-increasing. It depends if you're going from 1 to 0, and mostly you will be going from 0 to 1. So here, this is like 0 variation, something like that. And we would like to be continuous, because why have jump? We would like for the increments to be independent. So from here, I don't want to. I would like to have independent samples. And the last thing is decreasing and continuous. Yeah. But that's not the case. You can't have all 3 of these properties together. You can actually have 2 of them. With the Brownian motion, usually process will not be. You can even have some kind of process that goes from one place to another, but you can't achieve the monotonity. It will go up and down like this. It will never be non-increasing or non-decreasing. The gamma process is with independent increments and is non-decreasing or non-increasing, but it's not continuous. It is paths like this. So you do random jumps with random length, but it's not continuous. And the other processes, for example, can process that when you start, you generate a random sort. So you can have like many sorts, but as soon as you are in the trajectory, you will stay on that. And there will be an example of a process that will be, this one will be non-decreasing and continuous, but it's certainly dependent because when I'm observing the process like here, I will take it all the time. So, this might not be a bad model because you may have a component that is better or worse and it's throughout its the life cycle. It stays the same, so it's a reasonable model, but you can't have all three of these, which is just a disappointment. So this looks like a topic from optimal component theory, and if you have something like that, then you usually work in some kind of setting like this. You have some value function, but if you give it the state of the system, that it will be the x here. This is the policy, the control variable and time. And if you give me these three variables, I will give you the value that it's having. So, and some kind of, because we are running the process across some time, and we will have to, we will want to maximize the value function. So we will integrate like this. So maybe, because this will be the random case, this will be the deterministic case, but maybe the expected value might be some kind of similar to the deterministic case, and this is so the idea was that maybe we can do it on the path for expected values of the processes, but it will be a different story. We will see. So this is like a light representation. We have something that's called A out of N model, which this is 2 out of, yeah, that's 1 out of 2, that's the check Z's. Like, this means that the system is working if at least one component of the 2 is working. And we want to have a continuous degradation, which means something like that. Yeah. So we will have like a more complicated system. So the model that I ended up with, I decided on this model is the following. I have 2 variables. One of them is conditional, the component will be C. And we can see it as damage, and it could be these graphs. So we are starting with the new component will have the condition 0, and then as it ages up, it will its condition will get greater. And the second one is the control variable, and it's the performance. So on the first, and it's very simple relationship. The condition is integral over performance, and you can see it on the graph on the right. If you operate the component with flow capacity, meaning that P is 1, then it will age up in this fashion. If you have something more complicated, it will be another story. But it's the integral. And the other thing is that the output generated by the component is given by this formula, and this formula has 2 pieces. One is that the P is between 0 and 1, so on full capacity this is 1. And we get 1 minus the condition, which means that the maximum output that any given component can give at any time t is 1 minus its condition. So in the beginning it's 1, and it's the theoretic in time. Yeah, this with the relationship like this, I call it a linear model. If we give there some function g, usually the function we will be thinking about this function will look like something like this. It will be a function. I'm not sure if I'm giving. I don't think I'm giving you a definition, so I will write it down here. It's a function that is 0 and 0. It's one command and it's continuous. So if we have identity of the linear case, we will usually work with something like the square. This is something like that. Yeah. So the idea is on this next slide that this is the linear case, but components usually in practice you don't usually have this kind of behavior. That if you run them on full capacity, it's just and on half the capacity, it will be just scaling linearly. Usually, they have some kind of state where they are effective, meaning that if you can see it on the picture here, if you operate them exactly the same, the second one, of course, will get better because this. If you don't run it on full capacity, you will benefit from being a little lower in this. And so this might be some like example of a component that is running efficiently up until 80% of its capacity, and then it can run a bit after that, like from the 80% to 100%, but it's not effective because the deterioration is much faster, which will be the case. Well, that's the inspiration from industrial situation. So, okay. Yeah. Yeah. So, to give it into the context of the K out of N model, I'm giving the kappa out of N model. Why kappa? Because K does have to be a whole number. Kappa doesn't have to be a whole number. It can be anything between 0 and n. And then I want that you can interpret this equation, which will be the equation that we will be going to from now on, as that we want the system to operate as kappa are the components on full capacity. And also we have the condition which we said already that the performance will be higher than 1, so you have a upper limit on the performance, and this means that there will come a time when the components are too damaged to be able to have combined output of kappa. Yeah, and you can easily compute it. If all the components are in full capacity, it means there will be one inverse back with this, and you can compute that the sum of the damage of the conditions must be lower than something for the system to run. And the goal is to minimize the. Okay, what happens when the system isn't operational? It means that we must switch one of the components from one. That's the only thing that we can have as a maintenance action. We can just switch one for a new one. And here is some example. This is the performance how we operate these, and these are the conditions. So we start with two new components, then we run the system, and as soon as they can't handle it, we just throw away the worst, the more damaged one, and we start over. And the number of exchanges in the time unit is the efficiency. So, yeah. You can tell me here already in half of the presentation, and I just introduced the model. That's the problem with my model. That this is the thing I'm fighting a bit, is that I should have taken some kind of model that I read about somewhere and then tweak it a bit. But I wanted to solve something that I was thinking it will be easy, and I ended up with 15 slides just explaining the model. So don't worry, there will be some mathematics going forward. So now that we have a model, it might be interesting. Well, my first thoughts were that when I have such an easy model that it's linear, it doesn't depend on how we operate it. It will be always the same. So this is the case when you are in the 1 out of 2 model, meaning that you have 2 components, and in the beginning, this is what I call symmetrical control, meaning that every component outputs half of the combined output, and you can see you have 2 new components, and you can start at 1/2, which is enough to fulfill the condition, and as they get more degraded, you have to treat them higher once they reach the point that they are going to maximum capacity and they can't fulfill the condition. You will switch both of them for a new one. That's one of them, and this gives an average number of replacements per unit time. Some misplaced bracket. 8 is divided by 3, it's 2 something. Then we have asymmetrical control, which means that we also start with the new components, but we will make the first one go on full capacity, and the other one is just doing the rest of the output, and it's much better. It's to do something. So it's not the same. And in some case, in some sense, the symmetrical control is the worst one, considering the reasonable controls. If you don't, I don't know, discard new components right after you start, and then doing symmetrical control is the worst one. With a linear model, it's pretty easy to after all these years, it's pretty easy to count everything you want, the trajectories, the strategies, and everything. So we will stick a bit around this, and this is how it's done. So we start with the condition of the combined output. That's the first line, and we use because in this scenario we have the model is that the component, at each time is just integrate something else. So it's like this. So if we derivate both sides of the equation, we will get the derivative of the trajectory is it's like this. It's not. This is like a linear differential equation. It's not very difficult. You can basically, if you integrate on both sides, this equation, you will get a bit of rearranging. You will end up with something like this. We will take a look. Yeah, this is the other one, because once you plug something there, it's a completely different story. So we will. What is this graph? It's all the. Okay, so we have something like this. We have some components that are varying in time, and this graph is. There is C1 and there is C2 for the other way around. Yeah, it's the other way around, but it doesn't matter actually. And this means that when I'm starting with components, and as the time goes, I'm drawing the trajectory. And this is the space of all trajectories. If I start with two components that are new, I'm starting here, and if one of them is terminal full capacity, I will be going along with this line. If the other one, I will be going to this line. The red line is where they reach the end state when the system is not working anymore. So they are not capable of running the desired output. And these lines are how fast are they progressing through the system? If you take a look on the equation on the only equation on the slide is this one. This is the initial condition. Right, like this, in the beginning there is a condition, and they don't have to be new. Why would I think about not having new components? Is because when I'm switching them out, I'm always switching the most damaged component. The other one is some kind of initial condition. So yeah, and so on the right side there is time, and so if I fix the time, how far can I get? This can be seen on these lines. So yeah, it's because on the left side it is equation for a circle, and the circle has the center in 1, 1. We have two components. If it would be in for a component, it will be like the point when it has in dimensions and all the 1, 1s. And the diameter is shrinking with time. If I'm increasing time, then the diameter is shrinking. So this is where how can I can get to all of these points in the same time. So that's for the new component. The same equation. Okay. So what is how can we actually prove something like optimality? The way I was approaching it is using parallel controls. And so what does that mean? If I'm getting the periodic control, I will start with two components. One of them is new, one of them is slightly damaged. I will reach some kind of new. This is the end of the cycle. This will be the new component. For example, I will end up like this, and in the third round, I will have to, because it's end up somewhere here, and the other one is down there. Yeah, so like this is thrown away. Someone need to try it, so not. So I will throw like this one, and I will do the periodic control for two components. This is 3 periodic control for 2 components. So, and what I want to show is that if there is among controls that has the value of D, there exists one periodic optimal control, which is that I'm just having one cycle that's repeating over. And I said when I was last time trying to publish these results, I wrote something like it's not easy to demonstrate this is true. So since we have some time, I would like to prove it. At least for 2 components. Just to give you an insight how it works. So we have 2 components, we have some random kappa, no, it's not random, it's fixed, but it's some arbitrary plan. And we will like prove that the system. So we have a few things. We will use this notation that it will be the component I. Yeah. So we have components. Yes. This will be the first and the second one. And then we have a period of D. So the J comes through the cycles. And we will have two. This is the condition of component I in the cycle J at the beginning of the cycle. And this will become in the cycle will be the same component, but in the J is the time in the J cycle. So we have three things that we will combine together and get the result. First is the result about the time. I know that the time. Can you see it? So we know that I will maybe use this one, this equation. So we know that I will just rewrite the equation to our. So at the end of the cycle, the first component in the cycle J, it's time. There is one thing. Maybe I should mention that it's easier for notation if we start every cycle from the time 0 than to try to like remember all the times. So yeah, this equation holds also throughout the cycle, also in the end of the cycle. So this is the same holds for the second component. And this equals sign B. Yeah, the first component. And we will this is without also generality. We will also the more damage component is the second one. If we come, we could come up into something like this. You're very down for something that could be another part. It's just another notation. So the first component will be new. The second component. Yeah, so because the component is new, the first one will be new. Not the beginning of the cycle, so the first component will be new every time. So this is zero. And the second component will be just the this will be the first component of at the end of the last cycle. And it's basically the same. The first component C1 and that is in certain state, and we will then rename it as second component and move it to the next one. So now I want to extract the T. This is the time spent in the. So J, and I will also so the items 1 over 2 kappa And this will be the plus and this will be the minus. Now right now this is just one. This is plus 1 minus C2 plus C1. Of the last cycle. Now we have 1 minus C1 in the present cycle. Square minus C2
Čili pokud to není nová, tak to tady je prostě. Nějaký příčetné nula je to nula? Ne, to je konec toho class cycle is 0 or no? Tj minus 1. Tj minus 1. Yes. Is it 0? I don't think 0. Is it 0?
This is the, because I'm inside with J, and I start with this is the component, and this is the more domains, and it's the same.
But you want to prove that it is periodical?
No. The question is that's what I'm starting with. I can prove the optimality of method periodic controls. So I know it's periodical.
I thought that you are proving that it is periodical. So
I'm proving it. If it's periodical now,
then it's not periodical.
Yeah. Then I will.
Yeah.
Upon every periodical, or on the periodical controls, there is always one periodical. We need to do this. So, and what we'll do now is we just sum it, we'll use the periodicity. Because these and these is the same, just the index is different. And if I sum it all over, it's you can arrange it's finite sum, you can rearrange the numbers that we will get. This will get allowed, and we will speculate that the sum of the times you spend in all the periods is something like this. 1 over 2 kappa, and this 1 minus, and this is the state of the second component. So we have what are these? These are the state of the more damaged component. This one at the end of each cycle, and it's actually 1 minus. So it's how. This is actually so what we can take away from this is. First, we have to find the solution for. I don't really care about how I got there, which is actually the property of the linearity. But what I'm concerned with is how I end up. How there is one which is going away. This is the first thing. The other thing is easier. There is all the time the system will have to. Even at the end, the system will have to in each cycle. Will have to be like comparable. So this means that what this says is this is the first equation. first one, and if you run all the components into capacity, it means running having one, the one having the second one, you will actually get the equal to kappa. Otherwise, it's not operable. So, okay, this everything will just arrange it to get C1 will be lower than 2 minus C2. And this, it's pretty easy. And the other thing is that it cannot run on more than two capacity, so the second component, the time pj, cannot be greater than what it was in the beginning. All the time. That is because we can have the performance of the second component can be at most 1, and it's the derivative. So if the derivative is at most 1 will integrate. So if we combine these two together, we'll get something like this. Here we go. Insert this into this. Because this is the second component in the beginning of the cycle. Is the first one in the at the end of the last cycle. So we will get something like this. One, a minus 1. Yeah, and now again. Some of the words that I want you to like use this. So yeah. Yeah, I was sort of because it's not very hard to get it, but what we will do now is, since we have some here, we usually from these times, like after because we get this. So the sum I don't describe what this is. Okay, so what is this equation? It says that this is constant. You have capacity. This is constant from the beginning. So we have some kind of equation that is smaller than this one. But again, this is can like draw it as circles. So we have, what is this? It says that for the control to be admissible, we think that all this solution hold that the condition of the component to be strong way must be inside some kind of in two dimensions. It will be like this. It will be in the 2 minus 2 kappa minus 1. So it's something over here, and it will be this. So inside this hypersphere, there's only admissible controls, and we want the time we spend in these cycles to be as great as great. So what does that mean? We can the greater this will be from this is another problem, and the greater distance from the origin, which is also can be measured like this with these same numbers. The greater is this distance. The smaller is this, and the greater is the overall time of some inequality. So basically, we want to be as close to okay, I want to be as close as The point is, we want to be this component to be as large as possible, because this will be large, this will be small, and then will be large, and we want the time to spend where it's at. So we want these components to be as close as possible. But the point is, if we want to be as close as the beginning as possible, and also inside this sphere, and there is this point, which is on the line between point 0, 0, 0. This is d-dimensional, and the point 1. Which is the, so if there is a control that is periodic, then it's also one periodic. It's optimal. Then we have one other thing, and it is when this diameter is written somewhere here. And it may be that the sphere is in the origin is in the sphere, which will be the cases that we will mention. I'm getting the result that I'm talking about here is take kappa out of n. I have kappa out of 2. But the proof is pretty much the same. There is a few more sums to be handled, but it's pretty much the same. And again, it's this equation, but for a bigger system. So, and this is the case when if the kappa is small enough. This means that you don't want too much from your components. Actually, the origin might be inside the sphere. This is for kappa. If it's for n 2, the kappa is 1 over square root of 2. If it's lower, then it is possible to break every component up until the complete destruction when it's condition is 1. And but if the kappa is larger, then this 14 components is 0.7. Yeah. So if it's larger, then it's pretty much easy. You will. This is the one cycle. The thing is, once I put every handling the one periodic controls is pretty easy. So if I know that it will be one periodic, it's not a problem to find an optimal control, and it looks like this for kappa greater than 1 over square root of 2. This is for kappa 1, I think. And these are the, so basically what you should do is run one component on full capacity, do more damage, and the other one is just as slow as possible. And the other control is if you use the same strategy, meaning that you will the more damage control will get on full capacity, and then it's at some point it will get to the point when it's damaged completely. But the kappa is small enough for the other to go ahead. Which is interesting because it might be practical. If you have a system of components, maybe you won't have some extra components that you don't have to run all of them every time. So you can compute how much time you have. Actually, this time that you have the time to switch the components. For me, the switching is in like 0 time, which is the first model, but it's not realistic. You can. This is since you have some freedom here, because one of the components can run the whole system, you actually have like something like upper and lower boundary, which is weird because if one of them is like high, the other one is low, and the other way around. So if it's like upper boundary for one, it's lower for the other. But this is the operation where you can. These are the controls. When the more this is the control where you use the more damage component of capacity from the beginning. This is the control when you wait until it's necessary and then you have capacity. And everywhere in between there are controls that are admissible and also optimal. So this is actually the case that once you are inside, every control that eventually uses all of the components like lifespan is optimal. So we have more optimal controls, but there exists one that is one variable every time. So yeah. I also had a remark about how it's with non-periodic controls, because the idea is that if you can choose the DE whatever whatever you like. So it can be a little bit. So you shouldn't be doing that much mistake, omitting some non-periodic controls, which is the case, and I can prove it, but what I've seen in this it will be a bit more difficult, but it's doable. We can talk about it after the seminar. So, and now the fight I'm having right now with this is, of course, on the field of non-linear control, non-linear dependence. This is this G. So this was the winner. This is the non-linear, meaning that we will actually, right? If you will have the G that would go like this, then it will be the same as with in the linear case. Basically saying take the more damage component is running on full capacity, and the other ones doing the rest. The interesting thing might happen if you reward your components for not running on full capacity, which will be on the next slide. We have here 3 components, and since what is the G? The G is the strange like description. This is formula, but basically it's linear up until 0.8, and then it's quadratically going to 1, and it's smooth with if you compute it with these numbers. So what's happening here is you can see it on the upper figure that you should be somewhere around 0.8 with the performances, and then once it reaches, it's not like you can't control it like it forever. So once the time comes, you will have to take the most damaged component and just load it with everything and save the other ones. And it's not smooth, and this is just like from numerical reasons. So, and at this time, I'm getting. First, I wanted to make a stochastic model, and I had a lot of trouble already with the deterministic one, and now I'm continuing with the deterministic situation, and I'm roaming into calculus variations and these fields I was not familiar with, and it was always starts with me that with some naive idea. So. And also, yeah, that's one of them. So now I'm in a more complicated situation, and this means that the G is I think it's for most of these examples, the G will be just square. And so, in the linear case, it was there were these like circles, and if you were on what you needed, it will take that much time. It doesn't matter if you go that way or this way, but when you violate the reality, it stops. It's not the case anymore. So. What is this? Is like naive dynamic programming that you are in some kind of you are in a point and you try everything and you just remember how it went. So this is the solution. If I had the first component started slightly damaged at 0.1, the other one is new, and I want this component I will throw away, and I will keep the other one. And I want to keep the other one at 0.3, and this is the solution. I have all these points where I can go, and the green one is the optimal. And this is you can do it like this. This is the same approach, and it's pretty much working. The only problem is it's ineffective in computations, but yeah, that's the maybe. Yeah, and so this is my my favorite algorithm. If I don't know anything about the problem, I just use simulated annealing. Simulated annealing means that you're jumping around the state space, and you just with some when you are getting into better value, you always keep it. If you are going to lower value, sometimes keep it, sometimes not. That's the idea. And usually this is from the different pieces of the time. Schumann. Professor Schumann. So this is basically the proof that I like the algorithm so much that I want everybody to use it. So usually it's used for this is the traveling sensing problem basically. And so if you and this is also one of the trajectories, and the beautiful thing about this is you end up you give it a point where you want to be, and you just start and it's like trying to do something, and every time it starts long enough on some kind of trajectory, you will add points, and then you will get something slightly better. Yeah. So these are these naive approaches, and you can basically solve the problem with it, and you don't know nothing about it. Qualitative information about what's going on, and then we will have a few side of how it's done properly and how I can't really do it. So first things, maybe I will point out what is what I'm trying to solve here. Right, it's some kind of value function that I feed the state of the system. Should be like a vector of or I can something that is parallel. The initial state and the final state. At some p, I will feel like this. Maybe I'll fill in. So I have some initial state. Maybe enjoy it. This is from initial state, and I do some set that I can start and with array. With every point, I would want to have the key because this is what I'm designing. I want to, if I'm designing a control, I want to have information where I should go and how efficient it is. So. And this dealing just with if I give it 2 points, how efficient is it to get from one to another? This is what we are dealing with. And I have a few equations I will try to talk you through it. So this is contingent maximum principle, contingent, and it states that if the f is the vector of derivatives. If the system behaves like this, we have the parameter p we can choose, and if we choose it, then the system will behave like this. The r is the running cost, which is 1. We only value our system if it's operational, so it's 1. If it's not, it's 0. And then we apply Hamiltonian, which is defined like this, and this adds up a little vector function q, and the q is called state, and it states that the derivative with time of the constant is 0, which is good for us because in our special case, this actually means that q is constant. So it says to us, there exists constant. that is the second statement of the hodnota. But the optimal strategy, the P star, this is how we should operate it, will hold some kind of this maximal property. It's the maximum principle actually. So so we can get somewhere because if we because it's constraint optimization. It's constraint. We are looking for extremes using constraints. What is the constraint is written here. It's the same equation that we are looking from the beginning. It's the combined output should be kappa. It's written in this form. So we know that there exists a constant Q such as d naught, and you can, it's pretty good because you can get all the derivatives if you know. The only problem is you don't know lambda, and this is not the equation. This is the inverse function of the derivative of the g, which is computable for example for x squared. It's no problem. But if the g is somewhat more complicated, there will be some kind of equation, and we will have to solve it numerically. Okay. So if we would know that, then we can plug it like just back into the equation, and this is nice because if we would know lambda, then there is we basically can start a derivative. So we will have some kind of we got somewhere, but the problem is this lambda is changing. These QIs are constants all over the like all over the trajectory, but lambda is different every time. So if we make an assumption, so that we have some simplified form of g, is the x to the power of d, then it is even the g derivative inverse is multiplicative, so we can like get the lambda out and we can actually compute it. The problem is that you will have to have the solution to compute the lambda. So yeah. And so this is pretty much where I'm at. And in the never-ending cycle of I will just prove a little bit more, and then it will be finished, and then we'll open up something else. So I want to show you how this works. Yeah, maybe. So this is what you get when you have when you know. Yeah. So this is the start, and this is the yeah. So if you plug in some random like constants, the Q constants, you will get some trajectory that is optimal. If you want to move between those 2 points, it will be on this trajectory. Yeah, but you don't know how long it is. You can miss it, or yeah. So the first thing is if we can compute. If I give it 2 points and the trajectory goes through the points, and it is I can compute that this, if you have these 2 points, this one is the beginning, and this one is the end. So then I can compute the QIs, and yeah, it will be in the next slide, and get something get the trajectory goes through these points, but you don't know how long you should integrate. And after some time, I derive this equation, which is holding. And how do I know it's holding? It's because if I use it somewhere here numerically, it seems to do the job. Yeah, so this. And it would be, I don't think I can guess a formula that's complicated and do it exactly what I want to do, so it feels like it should be right. But the problem with the formula is that you have to know the solution and then integrate it to get the time. So basically how it's going around like now is that you complete it once and then you just derive from, you use this information and do it again. So that's the state I'm in, and I think you've heard enough today, and if you're interested in discussing something, I'm open to questions. And for me, I think what I should do is write it down, and I have to conclude a PhD and do something else for a bit. So that's all from me. Any questions? So if you're afraid, you can come visit me afterwards.